Most people think electricity is something you generate and then use. Flip a switch, the lights come on. But that simplicity hides a much more fragile reality. Because the world's power grids were not designed for the world we're forcing them to support today. They were built for predictable demand, centralized power plants, gradual growth. That design logic is breaking. Electric vehicles are adding massive new loads. Cities are electrifying everything. Heat waves and cold snaps are pushing demand to extremes. And yet, the grid is still expected to deliver perfect reliability, instantly, continuously, and invisibly. This video isn't about blackouts. It's about stress. Because modern civilization now depends on electrical systems operating closer to their limits than they were ever engineered to sustain. Every power grid is built around a concept engineers call margin. It's the buffer between normal operation and failure. The extra capacity that absorbs spikes. The redundancy that keeps systems stable when something goes wrong. For decades, that margin was comfortable. Demand grew slowly. Weather patterns were predictable. New loads were added cautiously. That margin is now being consumed. Not by a single event, but by thousands of small pressures stacking on top of each other. Electric vehicles charging at scale. Data centers running non-stop. Air conditioning loads surging during record heat waves. Each one makes sense on its own. Together, they push the grid closer to its limits, not occasionally, but constantly. And the most dangerous part is this. The grid doesn't fail gradually. It operates normally, right up until it doesn't. Power grids don't announce when they're approaching failure. They reveal it during stress tests. And few stress tests are as unforgiving as heat waves. When temperatures rise, electricity demand doesn't increase gradually, it surges. Air conditioners switch on at the same time. Commercial cooling systems ramp up simultaneously. Industrial facilities push harder just to maintain safe operating conditions. At the exact moment demand spikes, the grid's ability to deliver power quietly weakens. Transmission lines lose efficiency as they heat up. Transformers operate closer to thermal limits. Power plants themselves become harder to cool. So the grid is asked to do two contradictory things at once. Deliver more electricity, with infrastructure that is physically less capable of carrying it. This isn't a policy failure. It isn't poor planning. It's physics. For most of the 20th century, these conditions were rare. Heat waves were occasional. Demand spikes were short-lived. Margins existed specifically to absorb moments like this. But over the past decade, something changed. Extreme heat events stopped being anomalies. They became seasonal. In many regions, the grid now spends days, even weeks, operating near its maximum safe load. That's not how margins are supposed to work. Margins are designed for brief emergencies, not continuous operation. Living inside that buffer doesn't just increase risk. It erodes the system's ability to respond when something unexpected happens. And that's the quiet danger of heat-driven grid stress. Nothing looks broken. Lights stay on. Systems appear stable. Until one more spike arrives, and there's nowhere left to absorb it. For most of the grid's history, electricity demand behaved unpredictably, and that unpredictability was a strength. People woke up at different times. Factories followed staggered schedules. Cities rose and fell in power use gradually. Those natural offsets smoothed demand. They gave the grid time to respond. Modern electricity demand no longer works that way. It synchronizes. Millions of air conditioners react to the same temperature threshold. Electric vehicles begin charging at the same hour each evening. Data centers operate at full load around the clock, indifferent to time of day. Each of these behaviors is logical in isolation. Together, they compress demand into narrow windows that the grid was never designed to absorb. This is the hidden challenge of electrification. It doesn't just increase how much power is needed. It concentrates when that power is demanded. And grids don't struggle because they lack energy. They struggle because they lack flexibility. Electricity is uniquely unforgiving. Unlike fuel or water, it can't be stockpiled easily at scale. It must be generated, transmitted, and consumed in near-perfect balance every second of every day. When demand spikes faster than infrastructure can adjust, stability becomes a timing problem. And timing is where modern grids are weakest. Transmission lines can't be rerouted instantly. Power plants can't ramp infinitely fast. Storage systems remain limited and expensive. So synchronization doesn't just stress the grid. It removes the time buffers that once kept systems stable. The grid begins operating closer to a cliff edge, not because demand is reckless, but because modern life is increasingly aligned to the same clocks, the same incentives, and the same automated responses. And once that alignment locks in, small disturbances propagate faster, and recovery becomes harder. For decades, power grids were optimized around a single goal: efficiency. Generate only what's needed. Eliminate excess capacity. Reduce idle infrastructure. In a stable world, that logic made sense. Fuel was expensive. Demand was predictable. Growth was gradual. Every unused megawatt looked like waste. So grids were streamlined. Redundant transmission paths were deferred. Reserve margins were tightened. Backup systems were treated as costs, not safeguards. The grid became lean. And lean systems perform exceptionally well right up until conditions change. Resilience looks inefficient in normal operation. Extra capacity sits unused. Backup routes remain idle. Redundancy appears unnecessary. But resilience isn't designed for normal days. It exists for the abnormal ones. As grids became more efficient, they quietly lost tolerance for surprise. A single failure that once would have been absorbed now propagates. A delayed repair that once caused inconvenience now creates instability. This trade-off stayed invisible for years, because efficiency doesn't fail gradually. It works perfectly until the system encounters conditions it was never optimized to survive. Today's grids are facing exactly that scenario. More load, less slack, tighter margins. What looks like progress on a balance sheet often translates into fragility on the ground. And rebuilding resilience is far harder than removing it. Because resilience requires accepting higher costs, for risks that may not materialize immediately. That's a difficult choice politically, economically, and structurally. Upgrading a power grid is not a software update. It's a physical process constrained by land, law, and time. Transmission lines must cross hundreds of miles of terrain. Substations require space, permits, and public approval. Power plants take years to design, finance, and build. Even small upgrades move slowly. Environmental reviews take years. Legal challenges add delays. Local opposition can halt projects entirely. Meanwhile, demand doesn't wait. Electric vehicles scale in months, not decades. Data centers appear faster than transmission capacity. Climate-driven stress arrives without warning or permission. This creates a dangerous asymmetry. The forces increasing grid stress move quickly. The systems meant to relieve that stress move slowly. In many regions, planners know exactly where upgrades are needed. The problem isn't awareness, it's execution. Because grid expansion competes with other priorities: housing, land use, environmental protection, political risk. Every new transmission project forces a trade-off. Who bears the cost? Who accepts the disruption? Who benefits and when? These questions don't have technical answers. They have social ones. And social systems move more slowly than electrical demand ever will. The result is a grid that evolves cautiously, while the world around it changes rapidly. Not because solutions are unknown, but because implementing them requires coordination across timelines that rarely align. Power grids are no longer passive delivery systems. For most of their history, their job was simple: generate electricity, move it, deliver it. That model no longer works. Modern grids are being forced to become active balancing machines. They don't just supply power anymore, they manage behavior. Utilities now monitor demand in real time. They predict spikes before they happen. They intervene not by producing more electricity, but by reshaping how it's used. Pricing is adjusted dynamically. Large customers are asked to reduce load. Entire neighborhoods are nudged to shift consumption. In some cases, power isn't cut. It's delayed. This is the quiet evolution of the grid. Stability is no longer achieved by excess capacity. It's achieved by control. And control introduces trade-offs most people never agreed to. Who decides which loads matter most? Which systems are flexible? And whose consumption gets shifted when margins disappear? These decisions are increasingly made by algorithms. Optimizing flows, prioritizing demand, trading fairness for stability. The grid is becoming smarter but also more complex. And complexity, when paired with stress, introduces new kinds of fragility. The world isn't running out of electricity. It's running out of margin. Modern civilization depends on systems that work perfectly until they don't. And power grids are now operating closer to their limits than at any point in their history. This doesn't mean collapse is inevitable. It means trade-offs are unavoidable. Resilience costs money. Flexibility requires coordination. Stability demands choices that weren't necessary before. The question isn't whether grids will change. They already are. The real question is how deliberately that change happens. Do we redesign these systems with margin in mind, or do we keep pushing them harder until stress decides for us? Because electricity isn't just another utility. It's the foundation modern life is built on. And when foundations shift, everything above them feels it. If you like this video, and the way it looks beneath the surface of modern systems, Future Files is where we keep pulling those threads. Subscribe if you want to understand what's breaking before it breaks.